Saul, theoretical physicists have taken the work that you've done showing that the universe's expansion is now accelerating and now predict a pretty dismal future. That by this expansion, the accelerating expansion, that the universe will dissipate into virtual nothingness, where there may be one photon every trillion cubic light years or something. Having looked at the data yourself and having lived with the data, how can you help us really understand what the far future, the far, far future, will be?
I think one partly has to be a little humble in what it is that we understand at this stage, because what we've seen is, of course, a surprising change from the earliest universe, when we think the universe was slowing down, to what apparently seems to be the last half of the life of the universe in which it's been speeding up. And since we don't understand exactly why that speed up is happening, it's a little bit difficult to extrapolate with confidence as to what will happen in the long, far future. But if you go for the very simplest picture that we have at the moment, you would say, well, there's no reason that this shouldn't, what we call dark energy, that's causing, what that people use as the terminology for an energy that would cause the speed up, that shouldn't continue to dominate. And then you would expect the universe to expand faster and faster and faster into the far future. And that is the picture you were describing, one in which, basically you better do all your astronomy now because there'll be nothing else to play with, nothing to look at in just a few billion years.
All right, let's start with some basics and determine what we really know today from the earliest history that you can see in terms of the expansion of the universe. Everybody knows the universe is expanding. We've known that since the early part of the last century with the work of Hubble and many other people after that. So we knew it was expanding. We thought the expansion would slow due to gravity. And your work has shown that seemingly, at least at this point, it's not. But what can you tell us about the history of that in terms of looking back? How has this expansion tracked?
So what we think occurred, and of course this is based on the evidence that we've been able to pick up from both the supernova work that we've been doing and other data sets that you can put together, it looks as if the universe used to slow down.
The expansion was slowing down at some point.
Exactly. And
when, for example?
And we think further back than about 7 billion years ago.
So earlier than 7.
Exactly.
The universe is 13.7 billion years approximately.
Exactly. So about half of the time back in history,
it was actually
slowing down. And we think it's because back then the universe was more dense. So basically, all the matter was closer to all the other matter, and gravity was stronger, therefore.
The same amount of matter in a smaller amount of space.
Exactly. And, and of course, gravity is much, much stronger when things are close together than when they're far apart. As the universe expanded, though, all the stuff in the universe became more and more dilute. Distances between all the particles in the universe became further and further, and all the objects in the universe. And so gravity becomes weaker, and we think that what's happening is that you're beginning to see, underneath it, there was always this dark energy trying to expand space. And it wasn't winning because gravity was so powerful. But once gravity becomes weak enough, it takes over.
Because this dark energy is in every bit of space.
Exactly.
Or every
we think it
volume.
Pervades all of empty space. So the more empty space,
same amount. So the more space you have, the more absolute amount of this dark energy you have, because in every volume of space, there's the same amount of this dark, which is extremely small, but the more space you have, it kind of adds up.
Exactly. Until you have a huge enough amount of the space, and the gravity is now attracting things that are so far apart that it's pretty weak.
So you have two things going on at the same time, both of them leading to an accelerating expansion. Gravity is getting weaker because its mass is becoming more dilute. In the same mass in more space, and dark energy is becoming quantitatively stronger because you have more space.
And of course, it's a relative balance of how much in any given space do you feel one versus the other, and so you're almost saying the same thing both ways. One eventually is going to outbalance the other, and in this case, it will be the dark energy will eventually overbalance the gravitational attraction of the mass, and at that point, from then on, the universe will expand faster and faster. And of course, then the thing just builds on itself, because now the more you expand, the more of the dark energy you have relative to the mass. And so the more it wants to expand faster.
Well, this is a very critical point, and if you've said that dark energy seems to be winning for the last half of the universe, last approximately billion years, you should be able to see an increase in the acceleration. So the acceleration is accelerating even faster over the last half of the universal history. Can you find that? Is your data precise enough to find that?
These are exactly the kinds of things that now you want to look at in much more precision, and we have not yet got to the level where we can tell you how exactly is the acceleration and deceleration changing on the fine scale of of a few billion years, and this is what
fine scale to you being
exactly
billion year chunks.
Exactly, compared to the fine scale of the tens of billion years of the universe, or 15 billion total. So at that point, you are beginning to get to the point that you can. And in fact, what we're doing right now, and behind us, in fact, we have an example of a satellite that we're developing for this very purpose, with the idea being that you could make a measurement so precise that you can see the changes in exactly when did it stop decelerating, when did it start accelerating, and how much has that changed, that acceleration, over time.
And you would expect that the acceleration to be increasing.
In some theories. But it turns out that there are a wide variety of theories.
This is interesting.
And you could, in fact, come up with theories where it will do different things. In fact, since we don't know what causes the current acceleration, you could imagine that it will turn out to be a series of different new dark energies coming into play. Some might want you to speed up, some might want you to slow down. And that's the reason why you might not want to make a definitive prediction today as to what the fate of the universe will be at the end of the time, because we now know, which we didn't even know just a few years back, that you can have new things happening. And so if there's a new thing that happened 7 billion years ago, how do we know that there won't be another new thing that occurs in another 7 billion years?
Or what did happen is the combination not just of one thing, but the combination of several things that add together in some way that creates an effect, but once over time those different things that cause it disaggregate in their way and has a different
exactly.
effect. So it's not as sure as some people think that the universe will expand into oblivion.
Exactly, and you'll find some theorists proposing other theories where you could still end up in what you call a big crunch, where someday it may even slow down to a halt and collapse again. And that would be the ultimate finale to the story that we originally thought we were going to be looking for. And we thought we were going to be trying to find out if the universe was ever going to come to a halt and collapse in a big crunch. But what we've ended up with is a theory that looks like it couldn't. But then again, you have to allow for the possibility and look for evidence for theories, which will lead you one way or the other in the future.
And to do a precise determination of the effect of the acceleration in the dark energy over the last 7 billion years should be a very strong measurement on which that can perhaps select between or among the different theoretical models.
I mean, that's really the idea, that if you can see a detailed enough history, then we know that many theories differ in how what they would expect to see in this detailed history. Not every theory. We know that there will be some theories that are close enough to each other that they will be hard to distinguish. But what you want to do is pull together this evidence with other evidence out there that we're trying to explain all at the same time. And ideally, this will allow a theorist to have that aha moment where they say, I can now put all this together. Maybe I can explain the first fraction of a second when we think there was a sudden inflationary period in the universe. If all those things come together at one time and a theorist is able to say, I can explain now this detailed history and something else simultaneously, that's the moment usually that you start to believe that, okay, maybe we're onto something.
So the open universe is still an open question?
In my mind, I think most people would say that we can't know yet.